I actually have two questions. In 3.1, the very last question, I was a little bit confused with, and in 3.2, I got up to question number 8, and I haven't gone beyond that yet. That one's a little confusing for me.
Okay. Let me pull up 3.1 in my homework. Which problem was it you were looking at too?
It was the very last one in 3.
Okay. So we've got negative I to the 61st power in my problem. Let me share my screen here. So mine was negative, and one of these days I'll remember, negative I to the 61st power. Yours is probably something similar.
Yeah, I think so.
A negative raised to an odd power is negative. So we can just pull that negative out. That's a good start. And then we've got I to the 4th raised to some power. We need to divide 61 by 4. 4 goes into 6 once. 4 goes into 21 5 times. The remainder of 1. So 4 times 15 is 60. And then we have the remainder of 1, so that will be multiplied by I to the 1st power. And we do that because I to the 4th is 1. So we've got negative 1 to the 15th power times I. 1 to the 15th power is 1. So we end up with just negative I as our solution. And that seems to work pretty well. I should probably type that in before I get too excited. And I know you can't see it right now because it's not the shared part, but they did like that, negative I as the solution. Did that help?
I think so.
So
the examples, or the video examples, I think are showing you take I squared and you times it by whatever number makes it close to the, so for instance in this one it would be I squared times, or to the 30th power times I, and that'll give you the same result, right?
It will, yeah. Okay. The reason I don't like doing that one is because I squared is a negative 1, and now I have to think again, well, now I'm raising a negative to a power. What happens to that negative? So you basically have to do that twice on this problem if we use I squared. But if we use I to the 4th, well, that's just 1. Okay. And so, and 1 to any power is 1. And so I think it's cleaner to look at I to the 4th instead of I squared.
Okay.
I know they do the I squared. I just don't like it much because it's got that added negative in there that makes it a little tougher. So I go to the I to the 4th, but you're right. The video they have shows I squared. I just don't like that they do that. Well, I guess they can do what they want. I just don't like it for myself, I guess. Now let's take a look at that one from 3.2. This is number 8 on mine. I assume yours is similar. Solve the quadratic equation by completing the square.
Yes, that's it.
Okay. Well, one of the rules for completing the square is that the leading coefficient has to be 1. So I'm going to start by just adding 1 to both sides, get this constant moved over to the other side. And I'm going to factor 5 out. So I've got z squared plus 4/5 z. I'm going to leave some space. Now this equals 1 because we moved that 1 over. So thinking about this, if I were to multiply the 5 back through, 5 times z squared is 5z squared. 5 times 4/5 is 4 times z is the 4z. So now I've got 5 factored out. My leading coefficient inside here is 1. So now I can complete the square. So I take this middle term, and I like to do the work right below here. Take that middle term and I divide it by 2, which is the same as multiplying by 1/2. 4/5 times 1/2 is 4/10. Which, or we could, let's simplify that a little bit more first. Let's say, well, 2 goes into 2 once and 2 goes into 4 twice. So now we've got 2/5. 4/5 times 1/2, or 1/2 of 4/5 is 2/5. Now I need to square that and add that in here. So 2/5 squared is 4/25. We're just squaring both the numerator and the denominator. Now I added 4/25 inside the parentheses. Remember, everything in the parentheses is actually multiplied by 5, so 5 times 4/25, and let me write that over here. See, we can reduce this. 5 goes into 5 once and into 25 5 times. And so I've got 1 times 4 over 1 times 5. So I've really added 4/5 over here, so I need to add 4/5 to the other side. And that 4/5 comes from multiplying it by the 5 that I factored out in the first place. So now what I have, and I'm going to rewrite this, hoping to make it more clear, z squared plus 4/5 z plus 4/25 equals 1 plus 4/5. We know that 1, another way to write that is 5/5. And I did that so I have a common denominator, so I can add those together. And 5/5 plus 4/5 is 9/5. So now I can do a couple of things. I can divide by 5. That would clear out this leading coefficient here. And you know what? Let's go ahead and do that. I kind of like that idea. So I'll divide both sides by 5. Dividing by 5 is like multiplying by 1/5. Those are the same thing. So now those will cancel here. I'm left with z squared plus 4/5 z plus 4/25 equals 9/5 plus 1/5 is 10/5, and 10 divided by 5 is 2. You see how I got that 2?
Yes.
Oh,
Wait a minute.
I'm multiplying. I'm sorry, I'm multiplying, not adding. Sorry. 9 times 1 is 9, and 5 times 5 is 25. I shouldn't have added. I should have multiplied. I even wrote multiply, and then I added. I apologize for that. Okay, now the reason we complete the square is we have a perfect square trinomial here, which means term is a perfect square. It's z times z. This term is a perfect square. It's 2/5 times 2/5. This middle term is the square root of the first term times the square root of the last term times 2. So z times 2/5 times 2 is 4/5. So that's a perfect square, which means it factors immediately into the variable, and then that middle term divided by 2 and the whole thing is squared. Or it's the square root of this last term. So the square root of 4 is the 2, the square root of 25 is 5. And that will always be the middle term divided by 2. Always. And that equals 9/25. So let me now bring this up here since I'm running low on space on the screen. C plus 2/5 quantity squared equals 9/25. Now I've got a squared term here, so I need to take the square root of both sides to clear out that squared term. And I end up with z plus 2/5 equals plus or minus, the square root of 9 is 3, the square root of 25 is 5. So now I'll subtract 2/5 from both sides. So z equals negative 2/5 plus or minus 3/5. So if we do negative 2/5 plus 3/5, that gives us 1/5. Negative 2/5 minus 3/5 is negative 5/5. Well, that's negative 1. So 1/5 and negative 1 would be the two solutions by completing the square. It's a lengthy process, especially when that leading term is not 1. If the leading term is 1, it doesn't take as long, and we don't have to worry about this extra 5 out here changing that 4/25 into 4/5. And so I don't really like completing the square if that leading is 1. It makes it more complex.
That's where I got stuck, was with that leading 5.
Yeah.
And I couldn't figure out how to do that.
We've got another option. Maybe this will be better for you. Let me try something here. Rather than factor that 5 out, what I'm going to do is I'm going to fill this thing with white.
Okay.
So I can write over the top of it without losing that background stuff. All right. So one of the things we can do is we can take this after we add 1. Oh, got my 5z squared plus 4z equals 1. Now I'm going to divide everything by that leading coefficient. Just divide everything by 5. So with that first term, it just becomes z squared. The second term is now 4/5 z. I'm going to leave some space here, and we've got our 1/5. And now our leading coefficient is 1. So now I can follow the same kind of process. 4/5 divide by 2 is 2/5. We square that and add it in. Anything I add to the left, I have to add to the right.
Is that 2/5 or 2 or 1/5?
Yeah, 2 went into here once and 2 went into here twice. So it was 2 times 1 or 5 times 1.
Okay, got it.
I simplified that part. So now we have z squared plus 4/5 z plus 4/25. And over here, to get a common denominator, which would be 25, I'd multiply top and not by 2, top and bottom by 5. So I've got 5/25 plus 4/25. That's 9/25. And you can see we're at the same spot we were before.
Okay.
Perfect square trinomial again. The variable plus the square root of the last term, which is also that middle term divided by 2. Quantity squared equals 9/25. Take the square root of both sides. I'm going to bring that up here. We've got z plus 2/5 equals plus or minus 3/5. This is faster to divide by that leading coefficient, isn't it?
Yeah.
Subtract our 2/5, and we'll end up with the same results. Negative 2/5 plus 3/5 is 1/5. Negative 2/5 minus 3/5 is negative 5/5, which is -1. We got the same result, but we divided by the leading coefficient first. I would recommend you do that if you want to complete the square.
Yeah,
Oh,
that
you
one
know what?
seems easier to me too.
I said that, but then later we're going to want to keep it, just divide that out. Just leave the 5 in front like we had before. Later we're going to want, we're going to want this method, because we are going to, in 3.3, we talk about graphs of quadratics. And the graph of a quadratic, let me just show you real quick what that function looks like. And this goes back to those transformations we talked about. You've got a times x minus h quantity squared plus k. So here we've got our perfect square trinomial factored with a number out in front. And so having that 5 out in front is going to help you when we get to that section. Yeah, exactly. Because this is faster and easier. So, well, one of the things we do when we get into that section is we will be adding and subtracting on the exact same side of the equal sign. So that might help in that you can't really divide by 5. And then, of course, we've got another method that's not completing the square, and that's the quadratic formula that would give us the exact same result, which adds another bit of complexity to it. Let's see. We still have those answers. Fill this with the background color. Why it's not letting me select things right. There we go. And the quadratic formula, which you'll get to use here in a minute, as a reminder, it's opposite of b plus or minus square root of b squared minus 4ac all over 2a. And in the face-to-face class, when I have it, not the 142, but the 143, I show how that comes from completing the square. We don't really have the time in 142 to do that, so I'll just write it up there. But we've got a, b, and c right here. A is the leading coefficient, b is that middle one, and c is the constant. And so we can take those. Now I'm going to use z here since that's our formula. That's our variable. But that equals the opposite of b. B is 4. Plus or minus the square root of b squared minus 4 times a, which is 5, times c, which is -1, all over 2a, and a is 5. So we've got -4 plus or minus the square root of b squared. 4 squared is 16. -4 times 5 times -1 is a positive 20, all over 10. So this is -4 plus or minus the square root of 36 over 10. So that square root of 36 is 6. So we've got two options from that. we've got the plus option and the minus here in the middle. So negative 4 plus 6 over 10. Negative 4 plus 6 is 2. Over 10 simplifies to 1/5. We use the minus option. Negative 4 minus 6 over 10 gives us negative 10 over 10, which is negative 1. The exact same solutions we got before. And I think that's even faster. Now that is part of 3.2, so we haven't deviated from what we wanted to talk about today anyway. But we just saw 3 different ways to solve the exact same problem. And some ways work better than others, some are faster than others. Regardless, what we're trying to find is the values for z. Those are the zeros of the function. And they're called the zeros because if we were to graph this particular function, I've got it covered by white. See, I should keep that. So if we're graphing this particular function, it is a parabola, and we know that because the z is squared, and it is going to cross the x-axis at -1 right here and 1/5 about there. And let's see, I believe its vertex is going to be about here, and it's just going to open up both sides. So what we're finding with these answers are the zeros, the places that it crosses the x-axis. And that can be incredibly useful, especially if we're looking at a different parabola. Say we've got a parabola, oh, let's start here. It goes something like that. Well, it's got a 0 right here. And if this one were to continue down, it might have a 0 over here. But think about how we throw things or how we shoot things and how they fly in the air. They fly in a pattern much like this. It's very similar to a parabola. And so finding those zeros lets you know exactly where it's going to hit the ground. And that's why those zeros can become really important, so that we can understand how this parabola is going to interact with the world around us. So those become something we need to pay attention to. All right. So you asked for one question. I took it off into several different questions that not only helped you with that one, but also gave you some others you could look at, other methods of solving these problems. And we've had a few other people join us as we've been going. Does anybody else have any questions or any questions on any of these things we just talked about? I'm also going through and marking you present, so you all get credit for that. All right. So yeah, we needed to talk about ways to solve these quadratic equations. We had completing the square as one of those methods. We have the quadratic formula as another method. Sometimes it's easy just to factor directly. So if I had something, for example, like x squared plus 6x equals 7, well, to solve this, what I want to do is get everything equal to 0. And so I'll go ahead and subtract 7 from both sides. Then I'll talk about why I want it to equal 0. X squared plus 6x minus 7 equals 0. And I want that to be the case because thinking, just kind of setting that aside for a minute, if I have a times b equals 0, in order to make that true, a and or b has to equal 0. There are no other pairs of numbers we can multiply together and get 0 unless a and or b equals 0. One of those does. And so if I can have everything equal to 0 and change this formula around, or that equation around, so that I end up with two factors, one thing times another, at least one of those equals 0, and so I could set them both equal to 0 and solve for the variables. So with this one, I'm going to try reverse FOIL, which I generally say just factor directly. Keep my equals 0. So remember, with FOIL, we've got a couple of binomials that we're multiplying together. And the firsts always gave us our first term. Outside, inside always summed to the middle term. I should probably change these to put something that's a little better. Let's just kind of pick some numbers so that we can see how this applies. So first, x times x gave me x squared. That was the first part. Outside, inside, and last gives me the FOIL. Now the outside, inside always combine together. Well, I shouldn't say always, but when we have two binomials with the same arrangement with the first variable the same, they will combine together. So those we need to add to get the middle term. But the lasts always give me the third term, or the final term, and the firsts always give me the first term. So if I look at this first term here, this x squared, I need two things that I can multiply together to get that, and those will just be a couple of x's. Now I'm going to ignore the outside inside because those have to combine somehow, and I'm going to look at the last. It's negative 7. I need two things that I can multiply together to get 7. Well, it's prime. So my only options are 7 and 1. And now, because it's negative, one of these has to be negative and the other has to be positive. If this had been positive 7, both of these would have had the sign of the middle term. But because it's negative, one will be negative, the other positive. Now thinking about my outside inside, I want those to add together to a positive 6, so the larger number is going to get the sign of that middle term. The other one will get the other sign. So I've got 7x minus 1x gives me my 6x. So now I've got these two factors. Here's my a, here's my b. Those are multiplied together to get 0. So either x minus 1 equals 0, or x plus 7 equals 0. So over here, I'll add 1 to both sides, and x equals 1. Over here, I'll subtract 7 from both sides, and x equals negative 7. So either this is true, or that is true. And I will, either one of those, if I plug those into my original formula, it will give me a true statement. And so that's kind of just a direct factor method. And it works well if the factors of the last term can somehow be combined to give you the middle term. Now that what I just said only works if the leading coefficient is 1. If it's not 1, we can still do a direct factor, but it adds a little twist to it. Now let me show you another method that some students like. I'll go ahead and use the same formula. Oh, we should probably get one that's a little tougher. The weird x. Let's do squared plus 8x equals negative 15. So again, I want everything to equal 0, so bring it over to the other side, to the left. So I'll be adding 15 to both sides. Now, a lot of people have heard of the AC method. We've already kind of shown where A, B, and C are. The AC method takes A, which is a 1, times C. And now I need factors that will add to 15. Well, that's 1 times 15, or 3 times 5. Or negative 1 times negative 15, or negative 3 times negative 5. And I need the combination that will add to B. Well, it's that one right there. So what I'm going to do with this method is I'm going to split that middle term using those factors. I'm going to use the plus 3. Now the 5. And so I've split that middle term into these two, based on the factors that I got when I multiplied A times C. So now what I do is a little factor by grouping. I'm going to group these things together. And out of these first two, I'm going to factor in x. That leaves me x plus 3. Because x times x is x squared, x times 3 is 3x. Out of the second binomial, I'm going to factor out a positive 5. When I do, I'm left with x plus 3. And it had better be the same binomial I got that first one. If not, I made a mistake somewhere. So now what I'll do is I'll factor out the x plus 3. I'm left with x plus 5. And now I have my a times b equals 0, so at least one of those equals 0. And so x would equal negative 3, or x equals negative 5. Those would be my two solutions to this particular equation. And I can plug those back in and check them, make sure they work. That works just fine. Now let's look at completing the square, which was how we started this discussion. I'll use the same formula. That's the x squared plus 8x plus 15 equals 0. I'll complete the square and we'll get the same result. So with this one, I don't want everything to equal 0. So I'll start by subtracting 15 on both sides, get it back to how it originally was. X squared plus 8x. I'm going to leave a little space here because I need to use that space. I'm going to take that middle term, the b, and divide it by 2. And then I take that quotient, I square it, and I add it in here. Anything I add to the left, I need to add to the right. And now I've got x squared plus 8x plus 16 equals 1. So now what I need to do, I have a perfect square trinomial, which means this first term is a perfect square. The last term is a perfect square. And the middle term, the product of the square roots of those times 2. So the square root of x squared is x. The square root of 16 is 4. 4 times x is 4x, times 2 is the 8x. So that's a perfect square trinomial. And it will factor into the variable and then the middle term divided by 2, which is the square root of this last term. That whole thing quantity squared. That equals 1 in this case. Now I've got the square root equals something, so the square, so I need to take the square root of both sides. Because the square root of a perfect square is just the base of the exponent, the base of the square. Square root of 1 is plus or minus 1. I need to subtract 4 from both sides. Positive 1 minus 4 is negative 3. Negative 1 minus 4 is negative 5. And I got the exact same answers we had up here. So that's another method that works equally well to find the solution to the equation, or the values of x that would make this true. So we've got completing the square. I should probably write these down. Give myself a lot of room. We call it this because we completed the perfect square trinomial. This method that I showed you over here is often called the AC method. And it's akin to a direct factor. The first method I showed was a direct factor method. Both work wonderfully well. Let's solve the same one using the quadratic formula. So I'll bring up another layer here. And I'll fill it with white so that I've got some space to work in. I wanted to keep the formula and that information. So we've got our formula after we bring the 15 over, x squared plus 8x plus 15 equals 0. The coefficients are a, b, and c. So a is 1, b is 8, c is 15. The formula is that the variable equals opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So now I can just plug in these variables. X equals the opposite of b. B is 8 plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So that gives me negative 8 plus or minus the square root. 8 squared is 64. 4 times 15 is 60 all over 2. So that's negative 8 plus or minus the square root of 4 over 2, or negative 8 plus or minus 2 over 2. We've got two ways we can take this. We've got the positive and the negative. So the positive route, we've got negative 8 plus 2 over 2, which is negative 6 over 2, which is negative 3. The minus route, we've got negative 8 minus 2 over 2. Negative 8 minus 2 is negative 10. Divided by 2 is negative 5. The exact same answers we got with the other two methods. Now you will find that the quadratic formula, the one we just did, will always let you solve for the zeros, even if they're imaginary. even if you end up with a radical, it lets you solve that wonderfully. The factor directly method or the AC method will not always give you the result because you can't always find factors that would let you split that middle term. And I'm specifically thinking of when the answer comes out to be imaginary, or when you end up with some radical in there. It's pretty hard to guess a radical as a solution. Completing the square works the vast majority of the time, but like you probably saw when you came in, when Phil and I were talking, sometimes that A value, the leading coefficient, is not 1. And so we're given the twist where we have to factor that out first. And that makes it a little trickier, but it'll work. Quadratic formula will always work. It does bring up something that I've mentioned here, and that is imaginary results. So results with an I in them. Quadratic formula here, and thinking about how we come up with I, the only part of this that affects that is that radical right there. It's the only part that will tell me if I have imaginary solutions, because that's where we would end up with the square root of -1. They call that the discriminant. And you will be asked to use the discriminant to find how many of what type of solution there are. The discriminant is that square root of b squared minus 4ac. I'm sorry, it's not the square root part. It's just the b squared minus 4ac part. Let me get rid of that radical. Okay. So that b squared minus 4ac part. If b squared minus 4ac is less than 0, so we've got a negative inside there. Now we're going to end up with two imaginary solutions. We'll have the plus I and we'll have the minus I. So two imaginaries if that's less than 0. If, let's see, I need some space here. Just figure that out. If the discriminant equals 0, so now we've got a 0 in there, we end up with negative b plus or minus 0. So that'll just be negative b over 2a. We get one real solution. Our only other thing to look at is if b squared minus 4ac is greater than 0. So that's a positive number under there. We would get plus or minus the square root of a positive. So we would have negative b plus a positive and negative b minus a positive. So that gives us two real solutions. So when you are asked to use the discriminant to determine the types of solutions, this is the answer that they're looking for. They don't want to know what the actual solutions are. They just want to know, do we get two imaginary, two real, or one real solution? And that all comes out based on whether or not the value inside the radical is positive, negative, or 0. So that's what we're looking at there when we're looking at the discriminant. But it will allow you to determine that portion. All right, we have 4 minutes left, and there's one more thing I want to cover from this section. So I'm going to go ahead and get that real quick here. And really weird equations like this. 2x minus 3 squared minus 5 times 2x minus 3 plus 6 equals 0. That looks all kinds of weird. I can go ahead and FOIL this first term. Just square that binomial. I can distribute the negative 5 through. It would work. It would get me there. But you know what? If I step back and kind of squint a little, it almost looks like a quadratic equation. I've got something squared minus 5 times that something plus a constant. So let's say, you know what? Let's let m equal 2x minus 3. That stuff that's being squared, the stuff in the parentheses. So now I have m squared minus 5 times m plus 6 equals 0. Now I have a quadratic. This one looks like I might even be able to factor it directly, because factors of 6 could be 3 and 2, and 3 plus 2 is 5. So I think I'm pretty good. M times m is the m squared. As I said, I'm going to use 3 and 2 as the factors of 6. Because it's positive, they both get the sign of the middle term. So check the outside inside. Minus 3m plus a negative 2m is a negative 5m. So we're pretty good there. Now I set each one of those equal to 0, and I get m equals 2 and m equals 3. Great. Again, I got those because I set this equal to 0. Now I know the solution for m, but I need x. That was in the original problem, so I'll bring those up here. When m is 2, I've got 2 equals 2x minus 3. When m is 3, I've got 3 equals 2x minus 3. Now I'll go ahead and add 3 everywhere. So I've got 5 equals 2x. I've got 6 equals 2x. Divide everything by 2. 2 divided by 2 is 1. And I end up with 5 halves equals x, and 3 equals x. I think that's faster than multiplying all this together, which we could do and prove that we get the same result. But if you see something that looks like it, kind of like a quadratic, only they messed up the variable somehow, go ahead and do a little replacement. Solve for the quadratic and then bring that back to your replacement to solve for the initial variables. I think you'll like the way that works. Quick recommendation. We've got y to the 1/2 minus 4 times y. Well, that's doing all kinds of weird things. 1/4 plus 3 equals 0. That looks really weird, but if we say let x equal this middle one, y to the 1/4, if you square y to the 1/4, it's y to the 1/2. So this becomes x squared minus 4x plus 3, and we're back to a quadratic. So really, we take that middle part right there, that's where we do our substitution. That middle part right there is what you use for the substitution. And we're out of time. It just goes so fast. Do you have any questions before we go? right. Well, like I said, super fast. This is recorded, so if you need to go back and watch it again, do so. Work on problems from 3.2 tonight. So if you have questions tomorrow, we can talk about it. And see if we can get through this whole section. We may not be able to talk about every section this week that's due. So it might also help if you look a little ahead. So if you have questions on that, we can talk about it. All right. Well, let's call it a day. And I'll see you tomorrow.
Okay, thank you.
You're welcome. Thanks for coming in.